The objective today is to explain what the Intel manual says about signed infinities and NaNs. So we're on page 101, section 4.8.3.3. It says the two infinities, plus infinity and minus infinity, represent the maximum positive and negative real numbers. That can be presented in the floating point format. So it looks like these positive and negative infinities are just for the floating points. So there's a question, in what context are we learning about signed infinities? Let's try to keep a perspective about us here. And of course you see right here, I'm just confused as to why we would have this, because I thought, the concept of infinity is inclusive of both positive and negative ranges. Well, according to Intel, the way they represent infinity is by a significand of 1.00000, and the integer bit may be implied, so that 1 is just not even there. Which makes sense, because if we're working with binary numbers, you'll always have a 1 in the significand. Well, they go on to say that the maximum biased exponent allowed in the specified format, so for example to 155, for the single precision format. So they say that infinity is always represented by a significand of 1 and then all those zeros, it looks like, in the mantissa. And they also say that this is the same way you represent the maximum biased exponent allowed in this format. And what format are we talking about? Single precision. So the signs of infinities are observed and comparisons are possible. Infinities are always interpreted in the affine, and apparently affine means this is a concept that is just allowing of parallel relationships. So infinities are always interpreted in the affine sense, that is, negative infinity is less than any finite number. So to recap, it's because you can make comparisons in programs, right, in code. And if you ever make a comparison of something to negative infinity, it will be always less than the number you're comparing it to. And the reverse is true for the positive infinity. So arithmetic on infinities is always exact. Exceptions are generated only when the use of an infinity as a source operand constitutes an invalid operation. So two sentences that are very confusing to me. So to clarify, let's at least make sure we know what the sentence is saying. What is always exact? The answer is arithmetic on infinities. I mean, I can make an inference as to what that could mean, and I'm sure you can too, but let me not, just so I'm not filling anyone's head with incorrect information. And for that next sentence, let's ask, when is an exception generated? And apparently that'll happen when you're using infinity as a source operand. And that part's kind of funny to me because, just imagine storing the concept of infinity. You can't, right? It'd be infinitely large. But in the world of computers, we have a way to represent that concept. Of course, in a finite way inside of memory. Well, they go on to say that whereas denormalized numbers may represent an underflow condition, the two infinity numbers may represent the result of an overflow condition. So first of all, that part is just very logical. If you have infinity, you have a situation where overflow could be happening. But if we're capping it, then that's a smart idea. And let's review normalized numbers real quick. This is a chart we looked at before, and it kind of blows my mind because when you're looking at an unnormalized number, that kind of looks like more of a normal number to me than when I'm looking at normalized, which is done in scientific notation. But if you think about it in the context of floating point numbers, what they're trying to say is this is the normal way to store floating point numbers. Denormalized is a situation that happens, and there's good reasoning for it, but when it's happening, all bits of the exponent are going to be zeros. And in this case, like it says right here, when you see all zeros in the exponent, you know you're looking at something that is in its denormalized form. It's a denormal floating point number. So a good question to ask in this moment might be like, when might you see a denormalized number? And it says right here in that first sentence, Denormalized numbers may represent an underflow condition. So if you think of underflow like the opposite of overflow, I'm thinking of a really small number, a number that is so small the exponent doesn't need to be raised to anything, that the number could just exist within those 32 bits we are given. When it says the two infinity numbers may represent the result of an overflow, that makes a lot of sense. Let's jump to Stack Overflow to read what this person says about representing infinity. They say that if all the bits of the exponent field are set to 1, right, the exact opposite of what we were just talking about, and all the bits of the fraction part are 0, then the floating point number is an infinity. And we're getting close to answering why we would have assigned infinity. Well, actually, I'm not seeing it here in the last sentence, so let me just go ahead and say we're going to sign them not just for comparisons, but when you're doing this arithmetic, you might need to keep the sign. Well, let's wrap up the section here. It says that the normalized result of a computation has a biased exponent greater than the largest allowable exponent for the selected result format. So I think all that sentence is saying is the reasoning for biasing is because there's not enough room in the exponent to show the numbers that we want to be able to show. So I think that's just a very simple concept we should know. Why are we using a biased exponent in that floating point IEEE 754 standard? Okay, for the next section, NaNs, that's not a number. They say that since NaNs are non-numbers, they are not part of the real number line, and in figure 4-12, the encoding space for NaNs in the floating point formats is shown above the ends of the real number line. This space includes any value with the maximum allowable biased exponent and a non-zero fraction. In this context, the sign bit is ignored for NaNs. So we don't need it at all. So the question is, which bit is unnecessary when looking at NaNs? So the IA32 architecture defines two classes of NaNs. You got your quiet NaNs and you have signaling NaNs. And a quiet NaN, QNaN, is a NaN with the most significant fraction bit set. And so a good question is, what is the most significant fraction bit for? We haven't seen that in the manual yet. Apparently it's so we know we're looking at a QNaN. And not surprisingly, an SNaN is a NaN with the most significant fraction bit cleared. So 1 for QNaN and 0 for an SNaN. Now QNaNs are allowed to propagate through most arithmetic operations without signaling an exception. So I bet that's where they get their name from. So question, where does the name quiet come from? It's quiet because it's not signaling an exception. But what does signal an exception is an SNaN. SNaNs generally signal a floating point invalid operation exception whenever they appear as operands in arithmetic operations. Now, SNaNs are typically used to trap or invoke an exception handler. They must be inserted by software, that is, the processor never generates an SNaN as a result of a floating point operation. So we can finish with that question. What are SNaNs used for? And seeing that term trap or invoke an exception handler just made me think of that like Elmer Fudd Bugs Bunny kind of trap. And after reading this, I was wondering, like, why would you want to do that? Is this some type of software sabotage? For what reason are we trapping or invoking exception handlers? Well, the manual will answer that pretty immediately, but I'll leave you on a cliffhanger. So you watch the next part 31 of this series, where we'll be talking about operating on QNaNs and SNaNs. Thank you for watching.